Your computer could have the fastest CPU and GPU in the world, but without enough of the right RAM, it will still feel painfully slow. And most people are making RAM mistakes that are costing them performance right now. But did you know there are actually 10 completely different types of RAM, each one working in a completely different way? By the end of this video, you will know exactly which one your system needs. Let's get into it.
DDR5 RAM. DDR5 is the latest generation of desktop and laptop memory. And what most people do not realize is that DDR5 does not just run faster than DDR4. It fundamentally changed how RAM communicates with the processor in a way that makes future performance scaling possible in ways previous generations could not achieve. The shocking truth about DDR5 is that when it first launched, it was actually slower than DDR4 in many real-world tasks, because the higher latency of early DDR5 chips canceled out the bandwidth advantages, which is why the first people who paid premium prices for DDR5 systems were disappointed. DDR5 runs at speeds starting from 4800 MHz and reaching over 7000 MHz with overclocking, compared to DDR4, which topped out around 3200 MHz in standard configurations, meaning DDR5 can theoretically move twice as much data per second between memory and processor. What makes DDR5 truly future-proof is its on-die error correction. DDR5 modules check their data integrity internally before sending it to the CPU, a feature previously found only in expensive server memory, which means DDR5 consumer systems are actually more reliable than DDR4 systems were.
DDR4 RAM. DDR4 RAM became the most widely used computer memory in history, powering billions of computers, laptops, and servers from 2014 until DDR5 began replacing it, and it remains the dominant memory standard in the majority of computers being used worldwide today. What surprises most people is that not all DDR4 RAM performs equally. A DDR4 kit running at 2133 MHz and a kit running at 3600 MHz are both called DDR4, but the faster kit can improve gaming performance by 15 to 20% in CPU-limited scenarios, something most buyers never know when they purchase. The sweet spot that PC builders discovered was DDR4 3200 MHz with tight timings. This combination provided performance close to the theoretical maximum that DDR4 could deliver without the significant cost premium of faster kits that provided diminishing returns. One shocking fact about DDR4 is that AMD Ryzen processors are unusually sensitive to RAM speed. While Intel systems show modest gains from faster memory, Ryzen CPUs can show dramatic performance improvements from faster DDR4, making RAM selection particularly important for AMD builds. LPDDR RAM. LPDDR stands for low-powered double data rate, and this is the RAM inside every smartphone, tablet, and ultrabook you have ever used, engineered around a single obsession that desktop RAM completely ignores: consuming as little electricity as possible. The engineering achievement of LPDDR5X is extraordinary. It delivers over 77 gigabytes per second of memory bandwidth while consuming a fraction of the power that desktop DDR5 uses, which is why your phone can stream 4K video and run AI features all day without draining a battery in an hour. What most people never realize is that LPDDR RAM is physically soldered directly onto the motherboard. Unlike desktop RAM that sits in removable slots, LPDDR cannot be upgraded after purchase, which is why buying enough RAM at the time of smartphone or laptop purchase is so important. Apple's decision to use LPDDR5 in unified memory configuration inside M-series chips completely changed what laptop memory could achieve. By making CPU, GPU, and memory share the same physical chip, Apple eliminated the bottleneck that previously existed when separate chips had to transfer data between each other.
ECC RAM.
ECC stands for Error-Correcting Code, and this is the RAM that runs inside every server, workstation, and critical infrastructure system where a single bit flip caused by a cosmic ray, electrical interference, or manufacturing defect could corrupt data or crash systems worth millions of dollars. The shocking reality that most people never consider is that regular consumer RAM makes mistakes. Random bit errors occur in standard memory at a rate that is statistically predictable. And in a home computer, these errors might cause an occasional unexplained crash. But in a hospital database managing patient records or a financial system processing transactions, a single bit error could be catastrophic. ECC RAM detects and corrects single-bit errors automatically in real time, using additional memory chips that store mathematical checksums, allowing the memory controller to identify and fix incorrect bits before they reach the processor, making ECC systems dramatically more reliable than non-ECC alternatives. What makes ECC particularly interesting is that AMD Ryzen processors support ECC memory in consumer platforms, something Intel deliberately disabled in mainstream consumer CPUs to protect their more expensive server processor business, giving AMD an unexpected advantage for users who need the reliability of ECC without paying server platform prices.
GDDR RAM. GDDR stands for Graphics Double Data Rate, and this is the memory that lives on your graphics card, engineered specifically to feed the GPU's insatiable appetite for pixel data at speeds that would be impossible to achieve with standard system RAM. The speed difference between system RAM and GDDR is genuinely shocking. DDR5 system memory delivers around 77 gigabytes per second of bandwidth, while GDDR6X on NVIDIA's top gaming GPUs delivers over 1,000 gigabytes per second, more than 13 times faster, which is why GPU memory requires its own completely separate memory technology. GDDR memory achieves this extraordinary bandwidth by using an extremely wide memory bus, while system memory typically uses a 64-bit or 128-bit bus. High-end GPUs use a 384-bit memory bus, meaning the GPU can access many times more memory simultaneously than the CPU can. The reason GPUs need such extreme memory bandwidth becomes obvious when you understand what they are doing. Rendering a 4K game frame requires reading and writing hundreds of millions of pixels multiple times per frame, 60 or more times per second, creating a data throughput demand that no system memory technology could satisfy.
HBM. High bandwidth memory is the most exotic and expensive RAM in existence, stacking multiple memory chips directly on top of each other in three-dimensional layers, connected by thousands of microscopic vertical connections called through-silicon vias, achieving bandwidth that flat memory chips could never approach. AMD first commercialized HBM in its Fury graphics cards in 2015, shocking the industry with memory bandwidth that dwarfed GDDR while using significantly less power. But the extreme manufacturing complexity made it prohibitively expensive for mainstream products. NVIDIA's most powerful data center GPUs, including the H100, use HBM3, delivering over 3.35 terabytes of memory bandwidth per second, which is approximately 44 times more bandwidth than the fastest consumer DDR5 system memory, explaining why AI training that would take weeks on consumer hardware completes in hours on professional systems. What makes HBM manufacture genuinely mind-bending is the precision required. Thousands of copper pillars, narrower than a human hair, must align perfectly between stacked chips, which is why HBM remains extraordinarily expensive and limited to applications where performance justifies the cost.
Optane RAM. Intel Optane was one of the most ambitious memory technologies ever attempted, using a completely new storage material called 3D X-point memory that was faster than NAND flash storage but slower than DRAM, filling a gap in the memory hierarchy that Intel believed represented a significant market opportunity. The technology that Optane used was genuinely revolutionary. 3D X-point memory could retain data without power like storage while responding nearly as fast as RAM, which Intel marketed as the solution to the traditional computing bottleneck between fast, volatile memory and slow, persistent storage. What makes Optane's story a cautionary tale is its complete commercial failure. Despite the genuine technical innovation, the performance advantage over fast NVMe SSDs was insufficient to justify the premium pricing for most workloads, and Intel discontinued Optane in 2022 after writing off billions of dollars in investment. The ghost of Optane lives on in the memory industry as proof that technically superior solutions do not automatically succeed commercially. The market for memory products is brutally competitive, and a technology must deliver compelling performance advantages at competitive prices to survive, regardless of its engineering sophistication.
Virtual RAM. Virtual RAM is not actually RAM at all. It is a portion of your storage drive that the operating system treats as overflow memory when physical RAM is fully occupied, allowing computers to run more programs than their physical memory would normally permit at a significant performance cost. The performance penalty of virtual RAM is severe and often misunderstood. Accessing data in virtual RAM requires reading from storage, which even on a fast NVMe SSD is approximately 10 to 50 times slower than accessing real DRAM, which is why computers with insufficient physical RAM feel painfully slow when virtual memory is being used heavily. Windows calls virtual RAM a page file, while Mac OS calls it swap, and both operating systems use it automatically without telling users it is happening, which means many people experience mysteriously slow computer performance without understanding that their system is desperately using virtual memory because they have insufficient physical RAM. The practical implication of understanding virtual RAM is simple. Adding more physical RAM to a computer is almost always the single most cost-effective performance upgrade available, because it reduces or eliminates the severe performance penalty that occurs whenever the system is forced to use slow storage as overflow memory.
Cache RAM. Cache RAM is the memory that sits inside the CPU itself, running at the full speed of the processor and storing the data that the CPU is most likely to need next, eliminating the performance penalty of retrieving data from slower main memory for frequently accessed information. The speed difference between cache and main memory reveals why cache exists. Main DDR5 memory has a latency of approximately 60 to 80 nanoseconds, while L1 cache inside the CPU responds in just 1 to 4 nanoseconds, meaning cache delivers data to the processor approximately 20 times faster than main memory can. Modern CPUs contain 3 levels of cache: L1 cache that is fastest and smallest inside each individual core, L2 cache that is larger and slightly slower shared between small groups of cores, and L3 cache that is the largest and slowest but still dramatically faster than main memory, shared across all cores. AMD's 3D V-cache technology stacks an additional 64 megabytes of L3 cache directly on top of the CPU die using the same 3D stacking technology developed for HBM memory. And the results shocked the industry when Ryzen processors with 3D V-cache delivered gaming performance improvements of up to 40% simply from having more cache available.
Unified memory. Unified memory is Apple's most significant architectural innovation in personal computing, eliminating the traditional separation between CPU memory and GPU memory by placing both on the same physical chip, allowing both processors to access the same data without any copying or transfer between separate memory pools. The traditional problem that unified memory solves is fundamental. In a conventional computer, data being processed by the GPU must first be copied from CPU RAM to GPU VRAM, and results must be copied back, with each transfer consuming time and energy that unified memory architecture completely eliminates.
The real-world impact of this architectural change is dramatic. Apple M3 Max with 128 gigabytes of unified memory can handle video editing projects, 3D rendering, and AI processing simultaneously that would require separate CPU and GPU systems with much more total memory in conventional architectures. What unified memory reveals about the future of computing is that the traditional separation between different types of memory, system RAM, GPU VRAM, CPU cache, is an artificial constraint of conventional chip manufacturing rather than a fundamental requirement. And as chip stacking technology improves, future processors from all manufacturers will likely move toward unified architectures similar to what Apple pioneered.
That covers 10 RAM types explained easy way. If this video helped you understand something new, subscribe to ByteSimple right now, because next week we are breaking down 10 SSD types explained easy way. And trust me, you do not want to miss that one. Drop a comment below and tell us which RAM type surprised you the most. See you in the next one.